Let's imagine we have customers database, and the way we store data in the database is we have one base customer type with a list of properties relevant to each customer type, and we have 4 specific customers types like company, government, person, and school, and each of a type has its own properties. Let's see what we have in the database. We selected from a base customer type plus from all customer specific tables. So here is a customer ID, tenant, status, and type, and each customer specific type table has list of its own properties, like company has registered name and trading name, government has like country and department and city, person has first name and last name, and school also has some kind of list of its own details. And the problem we're trying to solve here, we need to search data among all 4 customer types and use couple fields to search for the specific customers. For that, as a starting point, we already have an API. This is our start solution. We have an entry point. We have a request limit on the entry point, so we don't want to our clients struggle when somebody is doing search operations. Then we have 3 instances of our web APIs, which then read data from the Postgres database. We also have some other components, but they probably not relevant to our search endpoint. If we try to execute the search endpoint we already have here, let me refresh. Yep, search endpoint. We can set search term we're trying to get data from the database. And very important moment, we have 1 million different types, 1 million different customers in the database. So baseline for our search over 1 million is, let me try to execute this request from a Postman. This is a single request over the locally deployed database and locally deployed web API. Request takes 6 seconds in order to find a couple of results, actually this amount of results, among 1 million records. As we can see, all currently implemented search technique has been far from ideal. 1 million scans or 1 million rows search takes 6 seconds. Once again, this is only one single request. Nobody knows what will happen. Actually, we will see what will happen when we try to load test that. Let's check the implementation details. So we have our application and our customer search handler. What we do right now in our starting point, we do select, and then we union all each table specifically, and then do a where clause over 2 fields, name and another field, in order to try to search records. As we already see, the SQL statement is already not very optimal. We can play with this SQL statement, and starting point is 6 seconds per single search request. Let's try to imagine what we can change and how we can improve the search behavior. Obviously, the first way to improve search behavior is to optimize SQL statement. For example, here in our version 2 of the search endpoint, we can send where clause statement or filter operation inside of each customer type, and only then union all only searched results. That's the first optimization we can do. We can verify this request in a Postman in a search v2, same data set, same search statement. If we try to execute, we can see that only this improvement already shaved like 10x from our latency. Currently, response time is half of a second. Very good improvement. Same amount of result data. Everything works like, probably we can stop here, but I prepared 9 search techniques. This is our version number 2, and let's see what we else can do. The next idea to improve our search is to, instead of searching over 4 different tables, what we can do, we can denormalize our customer's snapshot and create only one table. Let's call it customer search. Place only fields we need in that table and search over like plain table with a simple like and the same search term. Of course, we need somehow populate this data. So let's try to see what we have in the customers search. This is a customer snapshot. No references, nothing, just customer ID and the fields we do our search statements over. So here is a search text, and when we do search over this column or over these columns, we don't need any joins, absolutely anything. So this is like a snapshot. In order to maintain this snapshot, we already have in our system like a messaging solution based on standalone worker process and message exchange over there, in this case, RabbitMQ message. So when new customer is created, we populate customer's snapshot via messaging. Let's try to execute our search version 3. Once again, single request over 1 million records with a search term. We already can see this one is almost as good as the previous one when we search over a couple tables. But let me spoil a little bit. This difference will be obvious when we start load testing instead of single test. So search version number 3 is a search over denormalized snapshot without any references and without anything. Works good as well. Let's see what else we can do. Search idea number 4 is to create special index optimized for search queries. This pure Postgres or data store magic, where we, over the field we are going to search, in this case search text, we create this trigram index. Let's try to execute search number 4. Once again, we can see that the search over specific Postgres index optimized for search takes just amazing 7 milliseconds per request, returning the same result. Very good optimization, just a pure magic from a Postgres team. Can we do something else? Probably yes. Let's see what we have. We have full text search. Full text search obviously is different from the like type of search. Full text search is usually may or may not produce different result. So let's execute version number 5 with a full text search. we look the same term, the same data set. Let's try to execute search version 5 over the full text. Let's see its implementation. Search 5, handler. Once again, we're looking over the customer search, but we use a little bit modified where statement. Let's execute search request number 5 in a postman. Its response 5, 8, 7 millisecond. Obviously, this is vector search, so results might be different, but in my specific case, result absolutely the same as using like statement. Cool. Let's see what we else can do. Search improvement number 6 is we instead of do search statements over the Postgres, we might use different data store. Let me check what we have in a scale. We have where it is OpenSearch service. This is standalone server with indexed data, and we populate this index from the database. Once again, we already have long-running worker, which can read data from the original data store and place into separate OpenSearch data store. Let's see implementation. We have search query 6. This is our request. We asking for results in the search database. Let's try to execute request from a postman. Request search version number what? Number 6, yeah. So search over separate instance of the search engine is 95 milliseconds, but we absolutely don't touch Postgres or transactional database. So this search uses different store and search optimized engine. Very good one. Let's jump to solution number 8. And this type of search is instead of using messaging in order to populate search snapshot, we might use database triggers and populate. Let's find triggers. So we catch mutation events of each customer type, and then we create a customer snapshot, but pure via database triggers magic. Let's check our database. What we have, where's our database? We populate another one. I call it customer events table. It's another one snapshot, only the data we need to search, but this data populated pure via the database logic. Let's try to execute search 8. 5 milliseconds, 12 milliseconds, looking over 1 million rows. Very good result. And finally, as soon as we already have database populating snapshot via the triggers and via the database magic, what we can try to do, we can create a read replica standalone database with database replication to the customer events. So the same schema, but read replica of the original database. That's search number 9. Let's try to execute this search. Of course, we have latency over database replication, but search results are amazing. We have 6 milliseconds, 7 milliseconds, 5 milliseconds, all good. Now, we've implemented 9 different search techniques, and we verified that all of these work from a Postman. Everything is fine. We even have some results, but it's only one single request. In order to understand how our search techniques work under the load, we obviously can use any kind of load testing tool. For my search, I will use case 6. I already prepared a couple scripts, and we have a testing scripts to verify each of the endpoints. We will run a couple test rounds. Each test round will execute requests within our rate limited requests for 1 minute. So let's try to execute our load test benchmark tool. First of all, in order to execute request, our testing tool try to generate couple of the authentication tokens in order to then reuse different tokens for the testing endpoints. Let's wait for a second here. Now, when we have all tokens already prepared and ready to be used, we will start our test scripts and we start testing search endpoint v1 for 1 minute in order to see how it behaves under the load. When version 1 load tests are finished, we already can see the problem we have. Average HTTP request is 43 seconds. We've been able to execute only 50 iterations. And once again, average, the request which used to take here just where it is search just 6 seconds, under the load turned to be in average 43 seconds. Very unexpected, or actually it was expected result. Next script will test version 2. With the version 2 already have result average half of second. We've been able to execute a little bit more iterations, but still have very much like unsatisfied result. Let's check search endpoint 3, which is search over the snapshot. It's already executed, average 6 seconds. HTTP duration 6, almost 7 seconds. But we already starting to be able to execute more requests. So 6 seconds per request, but we're able to serve more requests, which is something we can enjoy unless different scripts started. Version number 4, it's a trigram index. This is the first script which executed completely successful. So we have 14 milliseconds per request, and we were able to execute 470 requests per minute. And this limit is something what we limit on our traffic endpoint. So the maximum requests we can accept is during the testing within 1 minute, 477. So this is this trigram index and implementation of a search version 4. The first successful result we can basically use in our production search over 1 million. Let's see some other results under the load. Version 5 executed successfully as well. Average 13 milliseconds. And once again, all requests been executed. I will spoil all next search scripts will execute successfully with a different results. Let me continue execution and make a summary in the end. This is a snapshot of result from my tests of each search endpoint. Original search endpoint took 42 seconds. And here is result. Let me remind, here is results. So version 2 web API with a union and then filter over 4 database tables, 43 seconds per request, and we didn't reach our rate limit API, so it was extremely slow. Search to filter per branch per the table, per each table is like 700 something milliseconds, still far from being inside the rate limit. The normalized read version 3 is when we use only one table is 7 seconds, and we almost close to reach a limit of the requests and traffic. Next, trigram index, amazing, 15 milliseconds. Version 5, full text search via TS vector, 13 milliseconds. Standalone OpenSearch instance, 70 milliseconds. Searching over cache with a Redis, 5 milliseconds. Searching over the database snapshot populated via triggers, 17 milliseconds. And search over read replica, 14 milliseconds. Our end solution, what we needed to build in order to achieve these results. So we have our entry point with a rate limit, 3 instances of the API messaging solution keep untouched, but we have main database, main Postgres database, we have read replica, we have standalone OpenSearch, and we have standalone Redis. That's the way to search over 1 million records in very good time measured results. Thanks.